This is part 5 of the trig functions videos. We will once again review the unit circle, then use it to graph the tangent curve and look at the domain and range of that function. The unit circle is centered at 0, 0 with a radius of 1. So if I go from the center of the circle out to any point, that line is going to have a length of 1. I'm going to drop a vertical down and look at the base length of that right triangle that I created. The coordinate point is at xy, so the length of the base of the triangle is x and the height of the triangle is y. I have used my right triangle trig to recognize that that coordinate point can also be written as the cosine of theta, sine of theta. And what I want to look at today is tangent. So tangent of theta, when that central angle is theta, is opposite over adjacent. So that's y over x. I can also write this as tangent of theta equals sine of theta over cosine of theta. Because in our last two videos we saw that x was the cosine of theta and y is the sine of theta because my hypotenuse length is 1. So tangent of theta is sine over cosine, y over x. I can also think of this as the slope. So tan over theta equals rise over run, or change in y over change in x. So those are the ways that we use to talk about the slope of a line. And that's going to be really important for justifying the graph that we see when we start graphing the tangent function. Remember that we're using quadrant 1, which has positive sine and cosine as our reference angle values. So if I was looking at the tangent of 2 pi over 3, I know that that's going to have the same sine and cosine as pi over 3. The sine, which is the height, will still be positive, but the cosine would be negative if I were looking at 2 pi over 3. So looking at pi over 12 as my angle, you can see my calculations on the right side here. Tangent of pi over 12 equals sine of pi over 12 over cosine of pi over 12. I've just used the approximate decimal version of those because we don't have the exact value for either of those trig expressions. And we get around 0.2588. So I've graphed that over there. When my angle is pi over 6, I've got 1/2 over square root of 3 over 2. So I'm using the sine and cosine values from the unit circle. 1/2 divided by square root of 3 over 2 is the same as 1/2 times 2 over the square root of 3. So dividing by a number is the same as multiplying by its reciprocal. Notice that my numerator and denominator switched from that original root 3 over 2. And when I multiply that through, I get 1 over the square root of 3. If I wanted to rationalize the denominator, I could multiply by the square root of 3 over the square root of 3 to get the square root of 3 over 3. So that's just the version of this expression that has a rational number in the denominator, and that's approximately 0.577. Pi over 4, that's 45 degrees. So the sine and cosine, the height of the triangle and the base of the triangle are the same length. And so dividing something, something divided by itself is 1. So we've got tangent of pi over 4 equals 1. Tangent of pi over 3, notice that the slope of my line over here is getting steeper and steeper. So we're finally seeing a trig function that has a range that goes above 1. So we've got the square root of 3 over 2 divided by 1/2. When I rewrite that as multiplication by the reciprocal, I get the square root of 3, which is approximately 1.732. Looking at the tangent of 5 pi over 12, I'm using those decimal approximations again. I get about 3.732. And then when I look at pi over 2, the tangent of pi over 2, I get the sine of pi over 2 is 1, and the cosine of pi over 2 is 0, because the height of the triangle is 1, and the base of the triangle is 0. And I can't divide by 0. I can't have 0 in the denominator. So the output here, the tangent of pi over 2, is undefined. So I'm drawing this vertical dotted line in at pi over 2 to show that I have a vertical asymptote, or I have an input that doesn't give me an output. But you can imagine if I was in between 5 pi over 12 and pi over 2, I would have a pretty steep line that would get steeper and steeper and steeper as my angle approached pi over 2. So when I'm looking at this function, I see that I've got this shape here, and as my input goes closer and closer to pi over 2, my output is going to get bigger and bigger and bigger and bigger and bigger until it's pretty much infinity, or it is infinity. And then I'm going to get to an input of pi over 2, and suddenly I have no output. So we'll talk more about that when we talk about the domain and range. So I've just filled out the rest of the tangent curve for you. Can imagine if we rotate past pi over 2, I'm at first looking at a pretty steep line, which will have a very large absolute value, but my slope is negative. So I'm starting at a pretty big number, and then slowly as I rotate around, my slope becomes smaller and smaller until it hits 0 at theta equals pi, and then it becomes a positive slope again, although it doesn't start off very steep, and then it gets steeper and steeper and steeper and steeper and steeper until it approaches infinity again, which is when we're at 3 pi over 2. So I've got another vertical line there, and then we jump past 3 pi over 2, and I'm at a negative but large absolute value slope, which gets closer and closer to 0 until it hits 0 and then goes into the positive region. So we're just going to have this shape over and over and over again. We can see that this is quadrant 1, quadrant 2 where my slopes are negative, quadrant 3 where they're positive, quadrant 4, and then I hit my 2 pi here, and we get the same pattern repeating over and over and over again. So thinking about the domain and range of this function, I can have an angle measure that is anything I want, but for certain angle measures, I won't get an output. So the domain of this function is all real numbers except pi over 2, which is where I've got this asymptote, and 3 pi over 2, and 5 pi over 2. So what we're going to do is we're going to write it as pi over 2 plus pi n. So n is our variable that usually stands in for an integer. So if n is 0, I have all real numbers except pi over 2. And then when n is 1, I have pi over 2 plus pi, which is 3 pi over 2. And when n is 2, I have pi over 2 plus 2 pi, which is 5 pi over 2. So this is our notation for stating all multiples of pi plus pi over 2, so that we can, in written form, without listing an infinite number of things, say all of the x values that aren't in our domain. And then the range is all real numbers, because just thinking about one of these curves, it's going to start at negative infinity, and it's going to get bigger and bigger and bigger until it gets to 0 and then goes up to positive infinity. So the range, the outputs, can be anything. The next video will be the last for trig functions. We'll talk about transforming sine and cosine curves, and then you should make sure you're doing the problem sets and checking with me to do a retake.